Hello, I'm Jaeheung from Seoul National University. I'm going to talk about variable stiffness control via external torque estimation using LSTM. Physical interaction has become an important topic in recent years as the demand for service robots and collaborative robots is increasing. We have to consider contact with objects and environments and beware of unintended collisions. So there have been many studies on the external torque estimation and impedance control with torque-controlled robots. Impedance control is a very effective method, but we still have to consider how much impedance should be applied because robots must interact compliantly, but at the same time, they should perform tasks precisely. Our research goal is achieving high position tracking in free motion and compliant behavior in contact state by adjusting stiffness. Unlike conventional methods with fixed impedance or variable impedance based on robots' own states, we reflect external torque to variable stiffness. Also, we try to use only motor side sensors for low sensor dependency. Ordinary momentum observer with simple dynamics model estimates external torque that include motor uncertainty. So we use LSTM to compensate motor uncertainty. LSTM takes the history of joint positions and velocities as inputs and learns the function of motor uncertainty. After the training is completed, we can obtain pure external torque as equation 1. After the external torque is obtained, we designed variable stiffness that satisfies 3 simple conditions. The first condition is that the variable stiffness should be kept between 0 and maximum control gain to maintain stable operation. The second condition is that the variable stiffness should be a decreasing function to adapt to large impact. The third condition is that the variable stiffness should be continuous to prevent torque command from sudden changes. In this study, we designed the variable stiffness as equation 2. Many other forms of variable stiffness can be designed, but a simple form such as a linear equation is infeasible because it has a negative value for a large external force. For experimental verification, dynamics-based control method was used, especially operational space formulation considering joint elasticity was used for the task-based controller. In joint space experiment, it can be seen that the variable stiffness controller is better pushed against external force than a fixed high gain controller, and it returned to its original position very well as the high fixed gain controller. In the task-based experiment, it was found that variable stiffness control exerts low contact force during collision and shows tracking as great as a fixed high gain controller in free motion. As conclusion, we proposed variable stiffness control via external torque estimation using LSTM in this study. The proposed method was accurate and stiff in free motion while exhibiting compliance in contact state. External torque was well reflected to variable stiffness because LSTM network compensates motor uncertainty. Moreover, variable form of variable stiffness function can be designed and used under the suggested conditions. Thank you for listening.